Welcome to the AI Research Roundup. I'm Alex. Today we're looking at this paper trending on X, published on October 16, 2025, about 6 days ago. The standout result is an online generalizable 3D Gaussian splatting system that reconstructs over 50 views at over 10 FPS while removing 50% to 90% redundancy. The paper is titled SaLon3R, Structure-Aware Long-Term Generalizable 3D Reconstruction from Unposed Images. And as we will see later, the gains in speed and compactness are matched by strong visual and depth quality. In short, the method compresses per-pixel Gaussians into structure-aware anchors, refines them with a 3D point transformer, and adapts growth and pruning without camera parameters or test time optimization. Alright, the introduction set the stakes on speed and compactness. Figure 1 contrasts free splat with SaLon3R on a 50-image sequence, showing reconstructed Gaussians and rendered depth. The left panels run at about 2 frames per second, with roughly 5,000 Gaussians, which leaves noisy geometry. The right panels run near 11 frames per second with about 1,000 Gaussians, so depth looks cleaner and redundancy drops by roughly 90%. So Figure 1 showed the speed and compactness gains. Figure 2 presents the full SaLon3R pipeline that processes each unposed image and predicts camera parameters, point maps, Gaussian latents, and a saliency map. The saliency-aware quantization block compresses dense per-pixel Gaussians into compact anchors, which cuts redundancy while keeping geometry. A lightweight point transformer then refines anchor attributes and saliency by modeling local 3D structure. Finally, adaptive Gaussian growing decodes anchors into renderable Gaussians for online reconstruction. Alright, the pipeline had been laid out. Figure 3 compares novel view synthesis across several baselines, showing rendered color and depth from 10 context views. The method delivers sharper edges and more stable textures, which reduces ghosting and blur in cluttered indoor scenes. Depth maps align with object boundaries and show fewer holes, so surfaces look flatter and distances remain consistent. Results appear closest to the ground truth, while competing methods exhibit streaks and swollen geometry. While the previous figure showed qualitative sharpness, Table 1 reports novel view quality on ScanNet, and the method leads across view counts, with ours reaching about 22 to 23 PSNR at 10 views and keeping the best or near best LPIPS as views increase. The highlighted R's rows show consistent gains over pose-free baselines. Table 2 then summarizes depth, where ABS-REL is around 0.03 and delta 1 near 98%, while throughput stays above 10 frames per second with far fewer Gaussians. So, while the previous figure showed qualitative sharpness, Table 2 reports depth, speed, and Gaussian count across view counts. The R's rows achieve ABS-REL about 0.03 and delta 1 about 98% at 10 views, running roughly 10 frames per second with under 900 Gaussians. At 50 views, ABS-REL stays near 0.06 and delta 1 about 97%, still around 11 frames per second with about 3,000 Gaussians. Free splat lags, with ABS-REL near 0.35 and delta 1 near 90% at 50 views, and fewer frames per second despite more Gaussians. So while Table 2 covered in dataset depth and speed, Table 3 tests zero-shot performance on Replica and ScanNet++ from 10 views. The method reaches about 21 PSNR on Replica, with delta 1 near 0.92, which clearly tops pose-free baselines and improves depth error to roughly 0.71 absolute relative. On ScanNet++, PSNR is about 22 to 22.4, with absolute relative around 0.10 and delta 1 near 0.93, whereas FreeSplat shows higher error and lower delta 1. Wrapping up, 2 takeaways stand out. Structure-aware anchors, plus a lightweight point transformer / Gaussian redundancy by roughly 50 to 90%, and the system stays real-time over 50 views while preserving strong color and depth. The broader impact is faster, pose-free 3D mapping for robots, augmented reality, and edge devices. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.